Morning, everyone. So we finally made it to the end of this acid-base chapter, actually part 2. This one here, if you compare between part 1 and part 1 we had introduced a lot of the vocabulary, what did it mean to be a Arrhenius acid. We switched over to a Bronsted-Lowry definition with basically protons being tossed around. We have conjugate pairs. The conjugate acid is the one with the proton, the conjugate base is without the proton. The part 1 of this chapter here mainly focused on strong acids and strong bases. Because they were one-way arrows, we didn't need to use any ice tables, there was no equilibrium involved. In part 2, we actually studied more so weak systems, and I just was hoping to summarize through some of the main concepts. So we started off this part 2 of this chapter here with a section on hydrolysis. Hydrolysis is the name of a reaction with water. Pretty much we're going to take a salt. The salt is going to break up, and we're seeing the reaction between the salt and water. This part here was very, very systematic. What you would do first is you would dissociate the salt, break up the ion. You would cancel out any spectators. Spectators just sit around, they're just going to swim around solution, they don't actually react with water. And then the third step is actually you would just check the table. That seemed like a sort of, well, why am I suddenly looking at salts here? We saw later on with titration curves here, when we did a neutralization, we always get acid and base produces salt and water. It was that very salt that may end up hydrolyzing. So we just wanted to practice that hydrolysis part first. In terms of spectators here, for the positive side, anyone that is a group 1, so column 1 or column 2, those ones there are generally soluble, so that makes them spectators. Once those are in solution, they don't really react. For the negative side here, we're looking at the top 5 conjugate bases of strong acids. Because you're always going to have your data booklet with you here, pretty much if we have on the table, we have our strong acid section right at the top. We have 6 strong acids. Because they're strong, they're going to one-way arrow. We have things like chloride, HSO4-, right? We have these ones here. If these ones here are anions and they are the partners of a strong acid, because they're one-way sort of against them, they're going to have no ability to go backwards. But I just noted here, well, we had 6 strong acids, and yet we only count the top 5. Why don't we actually include HSO4-? It is true HSO4- here definitely cannot regain that proton and go backwards, but because H2SO4 started off as diprotic, this one here actually still has a proton, and it's actually still able to be an acid. We're going to find the HSO4- a little bit lower down on the table here. Again, on the acid side of the equation, this one here actually is a weak acid. This one here can toss away its second proton and end up still being acidic. So in terms of which ones do you ignore, they're the top 5. I can list them for you here. We have perchlorate, we have iodide, bromide, chloride, and nitrate. Only those ones can actually go backwards, right? And then depending on, once you cancel the spectators, usually if it's the positive ion that ends up hydrolyzing, it's going to end up becoming an acidic solution. If it's the negative, it's going to be the anionic hydrolysis, so it's going to be basic. So let's just try a quick practice question here. Let's take NH4F, and let's figure out, does this one here hydrolyze? This one here is a salt, so we're going to ionize it. We're going to break it up. This becomes ammonium ions, and this becomes fluoride ions. You check whether you have any spectators. Well, NH4 plus certainly does have a +1 charge, but this is actually ammonium. This one here is not actually a spectator. Similarly, the F- is not one of those conjugates of a strong acid, so in this case, both of them might hydrolyze. If neither of them hydrolyze here, the pH should be 7 at equivalence point. But since both of them will hydrolyze, let's find where these ones here are on the table. So NH4 plus is fairly down on the acid side. This one here, its ability to be acid, our table only lists for us Ka values, so that's perfect. I want NH4 plus to be the acid. It tells me the Ka of my acid is 5.6 times 10 to the -10. For fluoride, I actually find it on the base side, right? Fluoride has no protons to end up giving up. Fluoride can actually re-pick up the proton and end up forming HF. This one here all happens at a Ka of 3.5 times 10 to the -4. But remember, this is a listing of Ka. This is how good my partner is actually coming forwards. For me to actually calculate for my base strength and going in reverse, we need to go Kw divided by that number here. The Kb for F- is 1 times 10 to the -14. Let's divide my partner's ability 3.5 times 10 to the negative 4 in going in reverse here. 1e negative 14 divide 3.5e negative 4 gives me here 2.9 times 10 to the negative 11. So as I drop this salt into water, there was no reason for this to be acid or base, but the ions, the NH4 plus wants to make it acidic by 10 to the negative 10, and the F minus wants to make it basic by 10 to the negative 11. In this case here, since the Ka is bigger than the Kb, the acid equation predominates, so the overall solution ends up being an acidic solution. Okay? So that's how you end up dealing with these hydrolysis style problems. The next thing that we switched over to look at were Ka and Kb calculations. We saw that the question became so much harder when we are dealing with something that's weak. So let me just make a comparison here. Back in part 1 of this chapter, I might ask you questions like, can you calculate the pH of 0.50 molar NaOH? Remember, you're going to save yourself a lot of time here. Anytime you're given a chemical like this, ask yourself, what is this? Is it an acid, a base, or salt? In this case here, we would say it's a base, and this one here is a strong. So if it's strong, we know it's a one-way arrow. It's an alkali salt. It breaks up completely. It forms that spectator sodium ion and ends up giving you hydroxide. I had 0.5 molar to begin with. This one here is completely ripped apart to become 0.5 molar sodium, 0.5 molar hydroxide. Now, we had already said sodium is a spectator ion. That's not going to interfere. The hydroxide content is already 0.50. Reminder again, them just asking you to calculate the pH just tells you where am I along the ruler. This doesn't decide suddenly we're acid. In fact, we're going to be very, very basic. We would expect the pH to actually be bigger than 7. The question became suddenly harder. I'm going to leave that question at that point. The question became suddenly harder. What if I swapped it out on you? Same story. Calculate the pH. Where along the ruler am I? But calculate it of 0.50 molar NaCN. Okay. Again, you ask yourself the question, well, what is this guy? This one here, well, it doesn't have the H, it's not an acid. It doesn't have a charge, it's probably not a base. This one here is actually a salt. So NaCN would similarly break up to become Na plus and Cn minus. The Na plus we said was a spectator. Now we have 0.50 molar. Well, what's the big deal? This one here was a strong base, so we can one-way arrow, no need for ice tables. Unfortunately, Cn minus is actually a weak base. Because weak bases here typically have very small ionization constants, we're looking at an expression, an equation, that's something like Cn minus here reacting with water. Make sure you write out the complex equation so that I can actually track hydroxide. This one we suddenly need to use an ice table. So if I just sort of factor this through here, the cyanide is 0.50. Before any ionizing, we have no acid form, no hydroxide. We weren't given any information about the final situation, so we're just going to use x's, plus x minus x. We had 0.50 minus x. This one's going to be x and x. And then whenever we have this, we're ready to plug into the Kb expression. The Kb expression, I would still tend to write it out with the chemicals, so HCN times hydroxide, just to make sure all the chemicals go in the right places. I'm going to get Kb from the table. I need to go Kw divided by Ka of the conjugate acid, right? In this case here of HCN. I have my x values. This is going to be x and x. This one here would have been 0.50 minus x. This one here, we wanted to simplify the math. I didn't want to do a quadratic expression, so just important for you to write out the assumption. Let's assume that of this 0.50, so little of this actually breaks off. Practically, it's 0.5. And that's given the fact I know the Kb constants are actually really, really tiny. In some sense, we're saying here, we start off with 0.50. I know a little bit of it is going to fracture over, but so little actually fractures, it's meaningless. It's just going to be 0.5. Note, in this problem here, we're still interested in finding x. Actually, after you solve that way through, it was just a lot more work to get to hydroxide. For the strong base case here, we just went 1 to 1, 0.5. We're going to find that starting with equimolar of the weak base as well, it's not going to produce as much hydroxide. Back when we did part 1 of this chapter here, remember once you are able to find hydroxide, sure, it was a lot of work to get to that. You can navigate around here. You can get to H+. Pretty much the relationship was Kw is the H+ times OH minus, the self-ionization of water. You can then take pH is the negative log of H+, or you can go down the other way. I can go the POH If I want to watch the hydroxide concentration instead, that gives me POH, and then I can use the expression the pKw is the pH plus POH. Pretty much if we assume that we are at 25 degrees, the Kw is 1 times 10 to the negative 14, and the pKw is 14. That makes 7 the dividing line, and in that, it'll actually help you find out the pH for these solutions here. Okay, so that's something we definitely worked on in the section here. Then the next sort of big topic we did was the titration setup. Now, I know we talked about titrations already in part 1 of this section, but let's just rehash some key points. For titration, a really common technique to find an unknown concentration. Right? So usually what this entails, we're going to have a burette. Right? It doesn't really matter what you put in the burette. Remember, the 0 markers on top, the 50 ml markers on bottom. We've done a lot of questions where we had base in the burette. So let's drop in. We have a known concentration, let's say 0.1234 molar sodium hydroxide. And I'm basically using the sodium hydroxide to find the unknown concentration of acid. Let's say my acid this time is going to be question mark molar sulfuric acid. So this stuff here could be really concentrated. It could have a lot of H pluses around. Maybe it only has a few H pluses. We're going to be able to count how much H plus by figuring out how much volume I actually end up dropping in. Remember, for a burette, we're going to take a starting reading, bottom of the meniscus, V initial. I might be, let's say, at the 10 mark here. That doesn't mean that there's 10 in the liquid. I just read it once. When the reaction is done, I read it again, V final, and I'd actually take that difference to actually figure out what the volume that I needed was. And pretty much what's actually happening in solution, we're dropping in the hydroxide slow enough. If the hydroxide finds an acid and neutralizes, keep going. We're looking for the situation where I drop in that very last drop of hydroxide, it kills off the H+, and suddenly we hit something called an equivalence point. So we are looking for an equivalence point. An equivalence point is when the moles of H+ has exactly matched moles of base. This is when the stoichiometry is perfect. This is when there's actually no linear excess. If I look at the balance equation here, we're going to have H2SO4. It's not always a 1-to-1 ratio. So case in point in this section here, that actually has diprotic. There's 2 H's. I actually need 2 OH's to counterbalance it. Na2SO4 and 2 waters. Right? At the equivalence point here, we've just added enough base to kill off all the acid. All the reactants are actually gone. That would imply to you, usually, the equivalence point here should have a pH of 7. But we found a few situations here. You're right, at equivalence point here, we have no more reactants. It really should be, so pH should be 7, with the exception, well, if this salt here manages to hydrolyze, right? The salt here had no business being acid or base. Let's do that hydrolysis practice here. Well, Na2SO4 breaks up to become 2Na plus and sulfate. The Na plus we've seen a couple times here. This is just a spectator. It's just going to swim around in water, no real problem. This SO4 minus 2 is actually a conjugate of a strong, conjugate of a weak acid. So when you find it on the table, you actually will find sulfate has the ability to pick up a proton and actually reform HSO4 minus. So if I wrote out that equation for you in the complex form, the sulfate can actually react with water. It can actually hydrolyze. It's going to reform HSO4 minus. It's in equilibrium, so not by much, but it is going to end up generating some hydroxide. So while I would have expected at equivalence point, or what's called the stoichiometric point, it should be totally neutral. Now, we're not producing a lot of it, but this sulfate manages to toss in a few more hydroxide. The pH here is actually going to be slightly bigger than 7 at equivalence point. So when we started doing those titration curves here, this is just a nice memory aid. If I titrate a strong acid and a strong base, usually nobody wins. The pH is going to be exactly 7. If I titrate a weak acid and a strong base, we'll look at that curve in a little more detail. The strong wins, so the pH is actually bigger than 7, like in this situation. Or if we have a strong acid and a weak base curve, the acid wins. The pH is actually less than 7. That's just a nice memory aid for you. You still have to explain in terms of hydrolysis. So for the first one, the salt hydrolyzes, like I just demonstrated here. The SO4 manages to react with water to recreate some hydroxide. Hydrolyzes to produce hydroxide, or in the other case here to produce H+. Okay. Notice we never ended up doing a weak acid, weak base curve here. First thing, there were two separate equilibrium. It's not as easy for you to actually find out the equivalence point, but it's doable. Okay. We had saw when we did these titrations back in part 1, we needed to use a chemical indicator. Now an indicator here we chose was phenolphthalein. Every indicator has an acid form. It's in equilibrium with its base form. Right? The acid form happens to be one color. The base form happens to be another color, but we definitely need it to be weak because we definitely need it to be a shift. In an acidic solution, the indicator, the H+ is high, it shifts over to the left. The indicator is in the acid form. In a basic solution, the indicator is shifted over into a basic form. Every chemical indicator has its own chemical structure, has its own Ka value. We had done a derivation. Every indicator has what's referred to as a transition point or an end point. Careful, this is different from equivalence point. Equivalence point is when the reaction is done. It's when the stoichiometry is equal. The transition point and end point, usually on the indicator table, they give you a range for phenolphthalein between 8.2 and 10.0. It changes from colorless to pink. The transition point and end point, just for simplicity, we're just going to take the middle value. Now, in some sense, that's not very fair because the pH is actually a logarithmic ruler. So 8.2 to 9.1, that's your transition point here. That's actually going to be a smaller gap between 9.1 to 10, but so be it. The 9.1 here is called your transition point. That's when you're going to get a mixture of colors. That's when the acid form actually matches up to the base form. And we're actually looking colorless and pink. It's just going to be a pale pink color. At that point, we derive the relationship. The pKa of the indicator is actually the pH at this endpoint. So it's fair game for them to ask, what is the Ka of chlorophenol red? What's the Ka of bromothymol blue? You just need to remember, take the halfway point in this pH range. Every indicator will change color at a separate pH point. Find that middle value. That so far is pKa. You just anti-log negative that, and that gives you the Ka of the chemical. Now, it's totally possible why I'm emphasizing endpoint and transition point refer to the indicator. When I actually plot this out on a titration curve, let's say we take a look at our acetic acid, sodium hydroxide reaction as a titration curve. A titration curve essentially has a pH probe instead of an indicator. We have tracking the pH here as I slowly drop in that base, volume of base added. Right? Because this one here is a weak acid, strong base, we would expect the equivalence point is the base wins. The equivalence point would have a pH that's bigger than 7. Couple keynotes. Because this one here starts off as a weak acid, so in my Erlenmeyer here, it's a weak acid, it can't generate a lot of H+, we would imagine this one here actually starts out higher. So it's not going to be in the really deep pH 0, pH 1 or so that a strong acid would have. What you're doing then is you're slowly adding base. The base is slowly killing off the hydroxide. And we're going to see this steadily goes up. Anytime you have a weak system, we have an equilibrium. So a potential buffer system is set up. So a buffer system here, you can add quite a lot of base here. The pH does change, but it doesn't change all of a sudden. Once the buffer runs out, however, so this part here, we had called it a buffer region. Once the buffer runs out, however, that's when it suddenly shoots up. And why is there this sort of shooting up region here is we go very quickly from having that very last drop of H+, you drop in a hydroxide to kill off that last H+, it should very well be neutral, were it not for the salt, and then you drop in a hydroxide, and now it can't find any more H+, the hydroxide is basic, within a very, very narrow range, within a very narrow addition of volume, we've actually caused the pH to jump all of a sudden. Part of it's also because of the logarithmic scale here, as I get close to 7, it's not that hard to become more acidic or more basic. This one here would be the volume of base that we would read from the burette. In this case, if I did it as a curve, even if my indicator changes color, you still want to take down a few other points so you get a sense of how this curve looks like. The middle of that sudden change here is the equivalence point. And based on what we had said earlier, would you be able to predict for me, how come the equivalence point, the pH is actually bigger than 7? I thought at equivalence point, I've just added enough base to actually kill off the acid. That is true. If you take a look at the salt that's generated, we get sodium acetate and we get water. The salt here had no business being acidic or basic, but wait, it might actually hydrolyze. the Na acetate here, the Na is a spectator, so that doesn't do anything. It just stays swimming in solution. The acetate actually manages to steal from water, recreating acetic acid, and more importantly here, generating hydroxide in solution. So even though we are at equivalence point here, we are slightly above 7. An indicator like phenolphthalein, we want to choose an indicator that changes color roughly where we're looking. Let's say the equivalence point here is at a pH 8.5. Perfect. Phenolphthalein also changes color roughly between 8.2 and 10. When the indicator changes color, I know when to stop. You can totally accidentally choose another indicator. Maybe an indicator changes color around pH 2, pH 3. Experimentally, you can drop it in. Oh, the indicator actually changed color, but that, you see, the color change point actually doesn't indicate to me the point I want to stop. So the conclusion out of this one here is we always want to choose an indicator as you're designing an experiment. Choose an indicator with a transition point, with an endpoint close to the equivalence, close to the point that the stoichiometry is equal, close to the point that you wanted to stop anyways. Now we had done a few calculations with this. We took VB, we took half of that value, we got V half. We saw that these two numbers were important. We can call it pH half, the pH at volume half, and the pH initial. Those were actually the only two numbers that we needed to actually find the Ka. We would practice through this with a virtual lab here. Let me summarize for you. The pKa of the chemical is actually equivalent to pH half. And then if you want to find the starting concentration is actually x squared divided by the Ka plus x, where x is anti-log of negative pH initial. You can look back at that lesson to figure out that derivation. Okay. Last thing I want to review with you here is, what about this buffer system? Can you define what is a buffer? A buffer is a mixture, or it's a solution. It's a solution containing appreciable amounts. There's enough of it that you can actually appreciate. Appreciable amounts of conjugate acid and base. Okay. It has to be weak, so it has to be in equilibrium. And what's its job? To maintain the pH. Notice I'm not saying to keep the pH suddenly constant. It is still going to change. Maintain pH upon small additions of acid or base. Okay, so buffers need to be able to block both ways. Okay, so let's take a look at an acetic acid buffer. We start off here something weak because we need to have an equilibrium that can shift, it can respond depending on what the situation is. This weak acid buffer here, H+, and we have CH3, CO- like this. At first, if I just start off with, let's say, 1 molar weak acid, we just did a lot of Ka calculations here, you're not going to get a lot of H+, not going to get a lot of CH3COO. So far, I can buffer base. If you add hydroxide at this point here, the hydroxide will kill off some of the H+, it's going to then end up forming water. As it pertains to the initial equilibrium, it's going to force some of this acetic acid to actually shift over to try to recreate some of the H+. In Unit 2, we found Le Chatelier, it doesn't get us fully back to what we want it to be. However, if I actually add H+, let's say the next time you have an acidic beverage, something like that, suddenly the H+ wants to go up. We want to actually shift to the left. Unfortunately, we didn't have a lot of acetate ions. Once the acetate ions runs out, if you add a bunch of H+, that's just going to stick around. The pH is going to drop all of a sudden. So we cannot, or we're limited, we cannot currently shift left since the acetate depletes. Okay, it's gone, right? So for a buffer system, like we said, we have to have appreciable amounts, not just of the one side, but also enough of the conjugate base. That can be as simple as, let's add in a salt. Let's go potassium acetate. Well, where'd the potassium come from? Well, it's an alkali salt. Alkali salts are fully soluble. That's going to artificially beef up the acetate. It does already shift to equilibrium, but we can get to a point where we have good amounts. Usually I like having equal amounts because we can do a little bit more math with that, but even if this were, let's say, 1.1 and 0.9 molar, still a buffer system. And so, if you then add that H+, now that the acetate has now increased, I do have the ability to actually shift left and shift right. Let me ask you this. Is there a difference between an acetic acid buffer? Right now we have 1 molar, 1 molar. What if I diluted both sides? What if I made this 0.1 molar, 0.1 molar? Is it still a buffer? Okay. Well, to be a buffer, you need to have a weak system. It needed to be in equilibrium. It needed to be able to shift, which in this case here it does, no problem. We have appreciable amounts. Obviously, we have more. If I have 1 molar, 1 molar, just having higher concentrations can shift for longer. And in the terminology, we can say it has a higher buffer capacity. So if you look back at the titration curve here, while the pH is not going to be exactly the same in the buffer region, if I were this 1 molar, 1 molar buffer, you can actually add, so pH, I'm actually adding NaOH here. You can actually add NaOH to quite a degree. You can add like 0.8 molar, 0.9 molar. Well, I have a good amount of acetate. I can keep shifting to get rid of that H+. It doesn't let the pH climb all of a sudden. So it's important to note the pH does change, but very slightly. As you add hydroxide and actually pull it the other way, it doesn't let the pH drop by very quickly as well. Okay? So the buffer capacity is actually given by sort of how much leeway do I have on both sides that I can buffer. What if I only had a 0.1 and a 0.1? Well, I do have appreciable amounts. I do have both parts. That's why I need it to be a buffer. I can shift to some extent, but suddenly, let's say the H+ is now 0.2 molar. I've now run out of acetate here. That's going to suddenly shoot downwards this way. It's going to suddenly shoot upwards this way. The buffer capacity is actually very, very small if the concentration is lower. But nonetheless, both of them could produce a buffer here, and its job is to moderate the pH. It tries to keep the pH relatively constant. Okay. We did do a buffer calculation just for comparison's sake here. We calculated what was the pH jump, and basically we saw that it was very, very small. There was a sort of side section on sort of oxides. Pretty much from that section, all you need to remember is metals tend to form basic solutions. So even if I had just plain old sodium in water, this tends to form sodium hydroxide. The particular metal solutions that we're looking at was actually metal oxides. They call those metallic oxides or ionic oxides. So something like Na2O, similar to just the metal by itself. This one breaks to become Na plus and O minus 2. O2 minus here is actually a strong base, and this will end up forming hydroxides. So it's this reaction here. O2 minus grabs 2 water, one-way arrow, ends up forming 2 hydroxide. Oh look, basic solution. Non-metals tend to form acidic solutions. So non-metals tend to form, and usually this is just a multiple choice question. They're going to give you 4 chemicals. Which of these are acidic? Usually 3 of them will be one type. You just choose the other option because they can't all be right. So non-metals, we can do a reaction. Let's say carbon can react with oxygen and become CO2, right? Again, we're not necessarily worried about the non-metal itself. Let's look at the oxide. What if the CO2 ends up running into water? I mentioned this naturally happens in our atmosphere, and it ends up forming a chemical called carbonic acid. Notice that this one here has an H, and this one here can actually, in equilibrium, release H plus and release some more HCO3 minus. So metals tend to be basic, and non-metals tend to be acidic. Another word for basic is alkaline. Okay, so have another look over these questions here. Practice through your ICE tables. Be really comfortable with K and KB, and let me know if you have any problems. Thanks, guys.